What if I told you that one of the most basic things you learned in physics is wrong? Electrons do not spin. Not like a ball. Not like a planet. Not at all. And if they actually did spin, they would break the laws of the universe. For more than a century, we have tried to understand what reality is made of. Atoms. Electrons. Tiny particles moving inside empty space. But the deeper we look, the stranger it becomes. We are told that the electron has something called spin. The word sounds harmless. It sounds mechanical. Like a tiny ball rotating in space. But here is the truth. The electron does not spin. Not in any way that your intuition can imagine. If you tried to picture an electron as a small sphere rotating on its axis, physics would immediately break. The measured angular momentum of the electron is fixed. It has a specific value. But if that angular momentum came from real physical rotation, the surface of the electron would have to move faster than light. Faster than light. That is impossible. So the first thing we must do is abandon classical thinking. In 1897, J. Thomson discovered the electron and shattered the idea that atoms were indivisible. Suddenly, matter had structure. Later experiments revealed something even more shocking. The electron behaves both like a particle and like a wave. It interferes with itself. It exists in probability clouds. It does not orbit the nucleus like a planet orbits the sun. And then came another mystery. When scientists studied atomic spectra, the specific colors emitted by atoms, they noticed tiny splittings in the lines. The equations of the time could not explain them. Something was missing. In 1925, George Uhlenbeck and Samuel Goudsmit proposed a bold idea. Maybe the electron carries intrinsic angular momentum. Not from motion. Not from orbit. But built into its very existence. They called it spin. The idea sounded absurd. How can something with no measurable size spin? Yet the mathematics worked. And then came experimental confirmation. In 1922, Otto Stern and Walther Gerlach performed a remarkable experiment. They passed silver atoms through a non-uniform magnetic field. Classical physics predicted that the atoms' magnetic moments would orient randomly, producing a continuous smear on a detector. But that is not what happened. The beam split into two. Exactly two. No in between. No gradual distribution. Just two discrete outcomes. This was the first direct evidence that angular momentum in the quantum world is quantized. For electrons, spin can only take two orientations relative to a magnetic field. Up or down. Nothing else. This is not a limitation of measurement. It is a rule of reality. Later, Paul Dirac developed a revolutionary equation combining quantum mechanics and special relativity. He was not trying to explain spin. Yet spin appeared naturally in his equation. It was unavoidable. The mathematics demanded that electrons must possess spin 1/2. Not 1. Not 0. 1/2. This value is strange. In classical physics, angular momentum comes in whole numbers. But quantum mechanics allows half-integer values. And spin 1/2 particles behave in a way that defies common sense. If you rotate a book 360 degrees, it returns to its original state. If you rotate a classical object 360 degrees, nothing unusual happens. But if you rotate a spin 1/2 particle by 360 degrees, its quantum state does not return to its original form. It changes sign. Only after a full 720-degree rotation does it truly come back to where it started. 720 degrees. There is no classical analogy for this behavior. It reveals that spin is not about physical rotation in space. It is about how the quantum wave function transforms under symmetry operations. Spin is deeply connected to the geometry of spacetime itself. It arises from the mathematical structure of the Lorentz group, the symmetry group of special relativity. In modern quantum field theory, particles are not tiny solid objects. They are excitations of fields that fill the entire universe. The electron field exists everywhere. An electron is simply a localized vibration of that field. Spin describes how that vibration behaves when spacetime is rotated. It is not spinning inside space. It is responding to the structure of space. This difference is subtle, but profound. Spin also determines the behavior of matter. Particles with half-integer spin are called fermions. Electrons are fermions. Fermions obey the Pauli Exclusion Principle, proposed by Wolfgang Pauli. No two identical fermions can occupy the same quantum state. This single rule explains the structure of atoms. Each orbital in an atom can hold only 2 electrons. And those 2 must have opposite spins. Without spin, every electron would collapse into the lowest energy level. There would be no chemistry. No periodic table. No stable matter. The solidity of the chair you sit on. The atoms in your body. The structure of DNA. All depend on electron spin. Spin also creates magnetism. Even though the electron does not physically rotate, it behaves like a tiny bar magnet. It has a magnetic dipole moment. When many electron spins align in a material, the result is a macroscopic magnet. This is why magnets stick to refrigerators. This is why MRI machines can scan the human body. This is why modern technologies like spintronics exist, using spin instead of charge to store information. On cosmic scales, spin matters too. White dwarf stars resist gravitational collapse because of electron degeneracy pressure, a direct consequence of electrons being spin 1/2 fermions. Without spin, those stars would collapse completely. Even the fate of stars depends on this invisible quantum property. So what is spin, really? It is not a tiny object turning. It is not mechanical motion. It is not classical rotation. Spin is intrinsic angular momentum. A fundamental label of the particle. A statement about how its quantum state transforms under rotation. It is built into the fabric of quantum fields. It is required by the marriage of relativity and quantum mechanics. It is as fundamental as charge. As fundamental as mass. Perhaps the strangest part is this. We use a familiar word, spin, to describe something that has no classical counterpart. The word survives from history. But the reality behind it is purely quantum. The electron does not spin like a planet. It does not spin like a wheel. It does not spin at all. Yet without spin, the universe would not have structure. Without spin, matter would collapse. Without spin, you would not exist. Spin is not motion. Spin is not rotation. Spin is identity. And identity is woven into the deepest level of reality.